So it seems like this version has a problem, and it's crashing on the results. Oh well. I actually just started up PS Cross View instead. That will take quite a while as well. This is actually going to look at what processes are currently on the system, but it's going to look at it from different ways. So it's going to do it based on the normal process list, or scanning for processes, thread process. There's that PSP SID table that we talked about with Pluto, etc. So that's going to look at a bunch of ways, and then it's going to tell you whether or not a process exists in any given list. Steve, could you close that? Thanks. All right, so anyways, that was volatility. Both WinDebug and volatility can give you the capability to analyze the system from outside of the system. And so, well, actually, I'm going to kick it off just for use for my own purposes later when I want to play with this. Let's do a quick, actually, I'm going to have you do it as well. Let's do a quick just example of grabbing the memory from this running system right now. So we can grab the RAM, dump it to a file, and then we can do these exact same volatility commands for this running operating system. So make a new command, make a new command window. Go to desktop /rootkits again /moonsols. And tab completion is your friend. Desktop, tab, rootkits, tab, moonsols, tab. All right. And here we've got, so I said I had the commands in the slides for Win32DD in order to do things. And I said that the simplest form is just basically do Win32DD /F, and then we'll call this local.dump, or maybe host.dump. So the other one was the guest OS. This is going to be the host OS. And we're just going to dump it to a raw file. If I did, well, maybe I'll do it in WinDebug format as well. Just going to do /D/F. Let me go double check that that's the right command. Yep, /D/F. We'll put it in WinDebug format so that if you want to go into this host.dump with WinDebug, you could open crash dump and then open it up. So it's going to ask, you know, are you sure do you want to continue? And I'm going to say yes. Now it's just going to be grabbing all of the RAM and putting it onto disk. But, you know, if you were to show up at a physical system, this would be the way I recommend to, you know, if you don't have firewire capture available, I'd recommend, you know, put Win32DD on a USB drive, plug it in, start capturing the file, and capture the file back off to that same USB drive so you don't destroy any deleted data on the host system or anything. All right. So, all right, there's other stuff like, that should be, that's another typo, that should be SVC scan. Service scan in order to list. So actually it can parse out information about services within the VM, actually from the memory dump. So that's kind of interesting. So it can list the things like, so we can see here that it did find, where is it? There it is. You can barely see.
It's supposed to be Python call.py.
Yep. All right, that's again another one that I didn't correct. Yeah, so that's, can't quite see that, but Hacker Defender there is one of the things that it found from outside of the system. So whereas inside the system, auto runs will not be showing you that. From outside the system, it does successfully see all of the service control manager registry entries. All right, so thanks to running extremely early, my backup material comes in useful. So let's talk about kernel object hooking. Yes?
Before we get in too deep, so when I tried to do the dump,
Mhm.
it says it is unable to do the install driver.
Unable to install drivers. Anyone else seeing that error?
Blue screen.
Here's blue screen. Awesome.
Sweet.
Better blue screen than...
So that's the driver that goes and grabs the frame.
Something's working.
Yeah, okay, so I didn't talk about that, but, you know, my, let's say prejudice, my feeling on these topics is, I kind of mentioned this before, that you need histograms here in order to compare what services are registered on your system versus many other systems. So it's more like on a single independent system, it's very hard to say what should or shouldn't be there, right? We know this. We see things that have weird names, and we don't know whether those are Windows things or just third-party software, etc. So I really think that, and I'm going to try to capture some data to bear this out, that when you start looking across many systems and you just take all of the service control manager entries, for instance, and you throw it into a histogram and you say, okay, I had 7,000 machines, and of that, 6,950 all have this service. So that's a, quote, good service. But now I have 3 that have this service. And so that bears investigating when there's something that's a complete outlier in terms of a low count as opposed to a high count. So that's just what that's kind of referencing. I call it better living through histograms. All right. So, kernel object hooking. I had made reference to this towards the beginning when we were classifying type 2 rootkits, or type 2 stealth malware, when we were talking about the stealth malware taxonomy. And I said kernel object hooking is basically a subcategory of DCOM where you're specifically focusing in on function pointers in dynamically allocated objects. So you've got some objects, they're being allocated just in time. They're not something like the SSDT that it sits there and, yes, well, I didn't even say this before, but the SSDT data is actually within the module space of NT kernel itself. So it's actually within the kernel proper. But with code, these are data structures which are being dynamically created. They have some function pointer for some reason or other. Typically, they're being used for callbacks. So it's something where you put in a function pointer and you want some other component of the system to call you back at that function when some event occurs. And so in this particular rootkit.com thing, Greg Hogland talked about kernel object hooking, where he was basically just throwing out there like, hey, there's this structure and this structure and this structure, and they've all got function pointers. So potentially, if the attacker can redirect those function pointers to his stuff, he can find out, he can interpose and man in the middle on stuff. So the thing about kernel object hooking, as opposed to these other things, basically the reason this is in the backup slides and the reason why the DCOM section was fairly small is because kernel object hooking becomes definitely an arms race. There's no sort of generic mechanisms you can use in order to say, here's all the targets for kernel object hooking, and this is where I need to look in order to prevent it. Right? So for the import address table, there's only one location for a given module that the import address table can be. The SSDT is always in the same place. IDT and GDT, those are both pointed to by hardware registers. They have to be where they are. Kernel object hooks occur in dynamically allocated structures, which are just wherever in random locations on the heap. And so it kind of becomes a situation where if the attacker knows that this dynamically allocated structure is useful to him, if he's gone and reversed something, he says, okay, if I change the function pointer in this structure, now I can, find out when certain events happen and I want to filter those events. So if he can find that, but you don't know about that, because he's reverse engineered the things and we're, legally prohibited from, we as defenders are legally prohibited from reverse engineering things in some cases. that becomes one of those information asymmetry points where by knowing more than you, he can be someplace that he knows you can't look, or he believes that you're not currently looking. So, I want to talk about the one that I know the best first, and then I'll talk about two other ones. So, here I'm referencing a particular FRAC article. It was not actually trying to talk about kernel object hooking in the sense of changing function pointers, but I just reference it because it has a good description of how these k-interrupt structures work. And so the way it works is, all right, so this is a k-interrupt structure. Well, this is our IDT overall. So previously we just thought of the IDT as it's a big list of function pointers, and that's that. Whatever is being pointed to, that's the thing which has interrupts occur. They go there, and they're done, and it doesn't interrupt return. So in reality, Windows layers some things on top of the IDT in order to allow for multiple things to handle an interrupt. So in the case we're used to looking at, that's this top case. IDT entry points at some code, and the code executes, and then it returns. That's what I'm calling here a direct interrupt. In other cases, there may be a single k-interrupt structure that's not part of any list. There's not multiple things which want to hear about it, but something did dynamically register to find out about this interrupt. So when something, let's see, do I have it here? I should probably add it. There's a specific function you call on Windows. It's like IO register interrupt or something like that, where you call this function and you're basically telling Windows, I want to find out when this particular interrupt occurs. So, in some cases, there's interrupts where one single component of the system registered using this function and said, I want to find out when this interrupt occurs. And in that case, what you see is the interrupt points at this code section, which is tacked on to the end of k-interrupt data structure. So k-interrupt has some ... at the beginning. There's various things in it. Then there's a linked list. There's a forward link and a backwards link. I guess there's not that much above it, but there's forward link and backwards link, and then there's some more data for the data structure, and finally there's some code at the end. This code is copied from like KI interrupt template in NTOS kernel. There's like some template code where it always copies this blob of code into the end of a k-interrupt structure, and then it changes like 2 assembly instructions, which customizes it to this particular k-interrupt. So in the case where only one person comes and says, I want to hear about this, you've just got a single k-interrupt with no linked list. And in other cases, you instead have multiple k-interrupts where they're chained together using this linked list that's built into the structure. So let's see if I have, okay, yeah. So in Windowbug, if you were to do just the bang IDT command and without anything else, it's going to hide a bunch of entries, but then for a few of them, it's going to print out information. In a few of them, it's going to print out this sort of information. And the point here is, I was kind of making reference to it before, volatility right now is not aware of k-interrupts. Gmer is not aware of k-interrupts. I'm not aware of any tool right now which understands how k-interrupts work and how they're chained, except Windowbug. So Windowbug knows that these things exist, and what it does is, if it sees that there's a k-interrupt, it comes in and it says, all right, I can see that the literal address points at, for instance, this 816A7854. It says the literal address points there. But then it goes and it looks and it says, does that look like it's actually a k-interrupt structure? So it says the code points right here, but I'm going to check some number of bytes back and see if this has a header on it that says I'm a k-interrupt structure. If it does, then Windowbug goes and it parses out, then Windowbug goes and it parses through this code and it says, at some point within this other ... down here at the bottom, there's going to be a pointer at the actual function which is trying to be called, and then Windowbug will print that out instead. So let's get concrete here. All right. Yeah. All right, so here I'm just picking interrupt 73. Windowbug is telling me, okay, the literal address which the IDT holds is 816A blah, blah, blah. But it parsed it and it said, this looks like a K interrupt to me. That's why it has this parenthetical K interrupt at the end. But then it also told you the name of the function which it's transitioning to. It's saying this is ndis bang ndis misr. So the thing is, where it got that ndis symbol name from is that it knows that although this function actually points at some blob of code that's tacked onto a data structure, within that data structure there's a field called service routine. So service routine is the place where this interrupt actually points out to, and this is the thing which is trying to be called. So when ndis registered to hear about this interrupt 73, it said, I want you to call me back at F95 ECE blah, 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 which corresponds to ndis misr. And so this is a function pointer within the K interrupt structure where that's where you're actually going. And so if the attacker comes in here and he changes that, then the interrupt will eventually go to the attacker code instead of this code. Now, the thing is, if an attacker changed that, it wouldn't be particularly hidden in from Windowbug, for instance. So Windowbug knows to parse that field, go there, and print out what's there. So actually, in our VM, we had seen that interrupt 62 was being listed as hooked right now, right? And I believe that was due to, I think that was due to daemon tools. So int E is the only one that explicitly is being hooked by me. That's ShadowWalker, right? So I installed ShadowWalker, it hooks int E. And then I installed all that chaff, and I'm pretty sure that's daemon tools, which is doing these hooks. And so right now it's saying, all right, the literal address points to 8178.404, blah, blah, blah. But I can see that's a K interrupt, and the base of the K interrupt structure is here. And the service routine points here, but it doesn't know what that's actually pointing at. So it doesn't know any symbol that corresponds to 81B8, blah, blah, blah. And that's kind of suspicious to me, only because I've seen, what K interrupts look like normally, and for a clean system, they always point at some system component. Therefore, if there's anything in here where it can't find what it is, then that's suspicious. So this 62 and that 82, those happen to correspond to the two things which Gmer was saying were wrong, but I think it's because those should not normally be pointing at K interrupts. Those should normally be direct things. And because they're instead just pointing off at some dynamically allocated code, it can say, okay, those are, wrong. It's not actually detecting the fact that a K interrupt is being changed, but that's because there wasn't a K interrupt there before. So it's just detecting the initial change in pointer. So the simple case is something like these top ones where they're direct interrupts. They go directly to one thing. Slightly more complicated is where you have a K interrupt. And again, I said this sort of unclearly, but if the literal address of the code which is being executed is, for instance, 8178.4044, if that's the literal address, the K interrupt address is that address minus 3C, I believe. So when we're looking at this data structure, if the interrupt is transitioning to the code right here, if the interrupt is transitioning to this code, Windowbug knows that this data structure is stored like this, and so it knows that code minus 3C is the start of the interrupt, and that's why it's posting the address of the start of the interrupt, so that if you want to go in, you can then use Windowbug's DT command for display type, and you can say display memory at that location as if it were a K interrupt. And that's what I was trying to show on this next slide here. So we take some address, or this is the literal address, and if we use the U command in Windowbug for unassemble, it'll show us, okay, yes, there is code at that address. But if we then take this other underlined address, where Windowbug's telling you, hey, this looks like it's a K interrupt, this is where the start of the structure would be, you take that underlined address and you use DT for display type, You use underscore kinterrupt to say this is the type I want you to interpret it as. It's sort of like C casting, right? So in C, you can cast something to a particular data type. DT is sort of like you're casting this memory to a data type, and then it's printing it out. So it does DT, kinterrupt, and then the address of the start of the kinterrupt, and then it will interpret everything as if it were a kinterrupt, which means there's going to be a 2-byte type field, 2-byte size field. There's going to be this list entry, which is the linked list. There's going to be this service routine, which I said is important. That's the thing which is eventually going to actually be called. That's the callback within this data structure. There's also this dispatch address, which is another potential target of kernel object hooking. But we're not going to get into that too much. The reason why this is not as great of a target is because dispatch address always points to one of two things. In the non-chained case, it points here at the KI interrupt dispatch. And in the chained case, it points at like KI chained dispatch or chained interrupt, something like that. So there's only two values that should ever be there, and therefore it's pretty easy to tell if it doesn't point at the correct thing. But the service routine can really point anywhere. And so if the attacker is inserting himself, if the attacker is removing the service routine for NDIS, he can now hear about all the events that NDIS was looking for before they happen. And finally, at the very bottom there, there's dispatch code. And so this is 106 words worth of, yeah, it's kind of, down here, there's 106 words worth of data. And the first data is that, but that data happens to correspond to those instructions right there. So if you take that little endian order, do 5-4, that's this push right there. 5-5, that's that push right there, etc. So this is the interpretation of some memory location as if it were a K-interrupt structure. And there's the service routine, which is kind of the target for kernel object hooking. Now, that thing I was referencing up here, this K-interrupt, or this FRAC article, like I said, they weren't actually trying to do kernel object hooking. They were trying to do inline hooking inside of this blob of code that's attached to a K-interrupt. So what they said is, hey, I know how this K-interrupt structure works. There's this blob of 106 words worth of data, which is all just a bunch of assembly. I can go into that assembly and I can put a jump instruction, right? And I will find out when this interrupt occurs, it's going to go there, and I can just put a jump there, and I'll find out about the interrupt occurring, right? So you can do either an inline hook on this code, which I would call more like direct kernel object manipulation. I guess it's sort of a quasi, oh yeah, what I call it, KOI. Kernel object inline hooking. That's right. So you can either do kernel object hooking where there's that service routine is in here, and that goes off to some actual function. You can do target that service routine, target the dispatch routine, or anywhere in this code you can put like an inline jump instruction and jump out some other code. And like I said, I'm not aware of any rootkit detectors which actually check this right now, but in WinDebug, it will certainly tell you if in WinDebug, it always goes in, it parses this as if it were a K-interrupt, it takes that service routine field, and then it tries to figure out if there's a symbol associated with that. And so for your normal Windows code like NDIS and L.dll and NTOS kernel, there will be symbols associated with that. That's these things. Got NDIS right there. Got ACPI right there. Got serial right there. Serial right there, I-8042 PRT. So this right here, this is that keystroke handler, which we hook in the intermediate x86 class. In the intermediate x86 class, it wasn't aware of K-interrupts. So it just comes in and it says, all right, I see that interrupt 93 is what happens when there's a keystroke, and it just replaces the handler. It just replaces the IDT entry. If it wanted to, it could come in here and change the service routine of the K-interrupt, and then the IDT wouldn't change. Or it could put an inline jump inside of the K-interrupt code, and then the service routine wouldn't change. I mean, that's really, if you want something to be undetectable to WinDebug right now, you do that inline hook, and I think that's why the FRAC article went that direction. If you put an inline hook right now inside of the K-interrupt code, WinDebug's not going to print anything different than it does right now. Whereas if you're changing the service routine, that's why we have like this B1, 62, 82. You're changing the service routine to something that doesn't have a symbol. That starts looking suspicious. Yes. It depends on what you mean by handle the interrupt, right? It depends on whether they're, for instance, consuming data, right? So let's say it's something like that network packet thing that I was talking about before, where the NIC card says, hey, CPU, I've got data in my buffer, come grab it, right? If the first thing here was an NDIS component which goes out to the NIC card and reads in that data and puts it in a buffer, then yeah, obviously there's no data left for this guy to read in, right? But in other cases, if it's just like some event is occurring and multiple things want to find out about it, if they only want to be notified of an event as opposed to like they're going and grabbing data or changing some system state, if it's only for notification purposes, then yeah, multiple things can find out about it. But yeah, like you say, they can't handle the interrupt in the sense of consuming data or adding data or anything like that. So let's see the actual things which are chained here, for instance. So inside of your VM, you'll frequently see chained stuff. I think this is the one right here, vmci.sys. This is actually a VMware tools sort of, actually it may not even be with tools, but this is a VMware kernel driver, vmci.sys. That one. But we can see that based on the other thing that's here right now, this video port interrupt, I believe this is the interrupt which is being used for displaying video essentially on the system. And so the VM internally may want to know something about when a video event occurs, and then the normal component of the system may want to know about it. So the VMCI may be doing some back-channel communication to the hypervisor, for instance. I don't think this one is, but one thing may want to know about a video event, and another thing may want to know about a video event. But unless they actually change the video data, they're both going to see the same sort of interrupt event. And ACPI, I can't think of a good example pertaining to that. All right. So this was kernel object hooking, specifically targeting the k-interrupt data structure, where I'm saying the service routine of that is basically just a function pointer of the thing which actually goes and processes the interrupt. Attacker can replace that, or attacker can replace code inside the dispatch code. All right, here's another thing. There's a data structure called NDIS protocol characteristics. So NDIS is the network driver interface specification. I've mentioned this a couple of times already in class, but just think of it as the networking subsystem. Yeah, and it's an abstraction sort of system similar to how IRPs are an abstraction system. You can have different layered levels of drivers, each of which can layer above or below other things in order to intercept network communications at different layers. So the thing is, if you want to be an NDIS driver, if you want to conform to this network driver interface specification, you have to actually register a bunch of callbacks in order to say how you're going to deal with things that are traveling up and down the NDIS stack. So actually, I think I'm going to do a quick picture of this. Move lights over there. All right, so can't remember what's above TDI. So if you have network hardware down here, the way that the NDIS specification is supposed to work is that there are mini port drivers and there are protocol drivers. And the mini port is the type of thing which is supposed to talk directly to hardware. And so I should be clear again, this is all within the NDIS specification. So a mini port driver is an NDIS driver. It has some requirements of functions that it must register in order to handle data that's going to come to it. Protocol drivers, same thing, they're within the NDIS specification. They have some functions they need to register in order to handle data that's going to come to them. All right, so mini port is the type of device which talks to hardware. Protocol is the type of thing which implements stuff like TCP/IP. So TCP/IP.sys is an example of a protocol driver. Wireshark is also a protocol driver. All right, so the point is, all the abstractions for TCP/IP and things like that, those are available at this higher level TDI, which I can't remember what that stands for, Transport Data Interface, maybe. And so the only one of the, well, where was I going? Oh yeah, so the point is, any driver that wants to conform to the NDIS specification must register a bunch of functions to say what it's going to do when certain data comes to it. Data for send, data for receive, data for configuration, things like that. And the only one thing I wanted to say here is that there's also the notion of an intermediate driver, sometimes referred to as a filter driver in this domain. That there. This is an intermediate driver. An intermediate driver is basically layer themselves between existing protocol and mini port drivers by faking out one side to the other. So whereas the protocol driver expects to always be talking to a mini port driver, this intermediate driver says, yeah, I have a mini port driver. Go ahead and talk to this mini port driver. And the protocol level side says, yeah, you know, I have a protocol driver, mini port, feel free to talk to me. And so it's basically faking out either side of this conversation so that the information flowing across here is man in the middle again by this intermediate driver. So, you know, this can be used for things like firewall drivers and stuff like that. I should say the Windows, at least XP firewall driver is not implemented at this level. It's implemented at some other crazy level that doesn't really make sense. But yeah, these are sort of the three kind of main drivers you can have in NDIS, but really it all kind of boils down to there's protocol drivers, there's mini port drivers, and there's something that pretends to be both, only to communicate with each side and pass data between them. So this NDIS protocol characteristics data structure gets filled in anytime a new mini port driver loads. It needs to go fill in a bunch of function pointers into this data structure when it's registering to be a component of NDIS, because if you don't register to the NDIS subsystem, you're simply not going to get packets, right? So what I wasn't aware of, well, I had heard references to this in various talks, but I'd never actually seen anyone specify the details. So there's a nice blog post here at F-Secure where they're talking about MEBroot, that rootkit in the wild. And they're talking about how it hooks the NDIS protocol characteristics thing. So here's a view of the data structure, and you can see it's pretty much just a bunch of function pointers plus a couple of things for version and then also a name. So when a new driver is registering to be a component of the NDIS subsystem, it has to fill in a bunch of function pointers for opening adapter, closing adapter, send complete, all this stuff. And so if an attacker knows how this data structure works, they can do things like go in and say, change this receive handler, So whereas this received handler, this would say whenever a packet's received, go to this function, and it would go to, whoever's mini port. Over to the board, please. So it's basically, there's some thing like ndis.sys, which is managing everyone else who's registering. So it's like when you register a mini port driver, you're calling a function in ndis.sys, and you're giving it this big data structure where you're saying, here, call me back at these addresses when these type of events occur. So you're calling out to a function in ndis.sys. It's taking that data structure, putting it in some list, and when it finds out that a new packet is being received, it's going down that list and saying, okay, for this mini port on this hardware, it should be called back here. And so I don't think you typically see multiple mini ports across multiple hardware, multiple mini ports to a single hardware, but you do have, multiple network interfaces. You've got your virtual network interfaces for your VMs. You've got your NIC interface. You've got your wireless interface, things like that. So there can be many different mini ports that NDIS is managing for many different pieces of hardware down here, right? And so NDIS's job is to manage this overall abstraction layer to say that, if I see packets coming in here, I need to call back that mini port driver at that function. And if I see packets coming in here, call that driver at that function. So this NDIS over here has these data structures like this. And if the attacker knows how to go find these data structures, he walks to the appropriate place and he says, okay, I don't want you to call tcp/ip.sys anymore when you have a packet received. I want you to call me first, and I'm going to check if that's my packet. And if it is, drop it. And then, I'll do my commands or whatever, but don't pass it to the higher layer. Don't pass it to Wireshark, anything like that, right? So this is another thing that's actually being used in the wild. And so just by changing one function pointer, two function pointers, you can find out when packets are received and packets are sent, and you can become, a packet sniffer, for instance, as well as, hiding your own packets from the rest of the system by intercepting them, checking if it's yours, and then dropping it. All right, so that's another large target of kernel object hooking. And then another one that I found while I was just Googling around, and this is again something where they were talking and digging down and analyzing MebRoot, is object type initializer. So you can think of this like a data structure which holds function pointers for constructors, destructors, and accessors of an object. So there's a generic notion of an object, and then you've got this object type initializer which says, here's my function for my constructor, destructor, etc. So this is what the data structure looks like. And then inside of it, there are things like dump procedure, open procedure, close procedure. And this just says, for this particular object type, for whatever object this thing is associated with, so this can be associated with many different types of objects. Again, it's just an abstraction layer thing. For whatever this is associated with, if someone calls open on this object, then it's going to call this function pointer, and that's going to implement open for whatever open means on this particular data structure. For delete, same thing, open, close, delete, all that. And so if an attacker gets in here, they will be called instead of the legitimate things, and therefore they can see when the object's being opened. They can see when when parse is called, if maybe parse is sending back the data for it and things like that. So they can manipulate the data and, as usual, just get themselves into in the middle. So the one point I would make here is that I said kernel object hooking, it's definitely it's definitely where you get into the arms race side of things, where they're changing things that naturally change. And therefore, first of all, finding them is difficult in that in both of these cases, they're finding that this rootkit does this not by, running some tool, because most of the tools don't look at this stuff. They're reverse engineering the code, and they're seeing some change that it makes, and then they have to go back and say, why are they changing that? What is this actually doing? Oh, okay. That's an NDIS data structure, and it looks like they're, now intercepting packets and stuff like that. So this is sort of where we get into a situation where There aren't good generic detectors for this across all the different places where you could be, changing function pointers throughout the system and where they may be useful to attacker. All right, so at this uninformed article, you can find more examples of kernel object hooking where that's actually a really good article to read in general. It's trying to kind of create a taxonomy. They're calling it local kernel mode backdoors. So they were coming at it, I guess, from a backdoor sense rather than a code that hides sense. But still, it's really a lot of it is just rootkit techniques all being enumerated in that document. All right, so that was kernel object hooking. Does anyone have any questions on that before we go on? All right. So my quick divergence into, what shall we say? I don't know, let's call it self-promotion. All right, so now we're going to just quickly talk about a new type of attack that I found based on having drilled down in the intermediate x86 class when I, half of that material I already knew from OS class, half of the material it was stuff where I wanted to know it better, so I just said, okay, well, I'm going to put this in the class so I can teach it, so I'll learn it better. All right, and so I didn't really know that much about the segmentation level stuff and how it pertained to interrupts and things like that. But so the key point to remember when dealing with interrupts is that they are far pointers. It's a 16-bit segment selector and a 32-bit offset. Now, normally, when something like that keystroke logger we have in intermediate x86 class, normally when you hook the IDT, you just change the 32-bit offset because you know that the segment selector is pointing at a base of 0. So it's 0 plus your 32 bits equals whatever code you want it to vector to. So the thing is, and so I had this in my mind where I said, wait a second, if it's just doing the math to add the stuff up, why can't I just change the segment and then leave the 32-bit offset the same? And it turns out you can, and it turns out that most detectors are only looking at the 32-bit offset. So if you leave that the same, you change the segment base, you change the segment selector so it points at a different segment. That segment has a different base. That base plus the existing offset equals the attacker's code. Then you can successfully vector to new code, even though things like WinDebug, Gmer, VirusBlock, Ada, they'll all still tell you that the IDT is unhooked and pointing at that same 32-bit offset. Basically, they're not segment aware. And why should they be? Because typically people don't have to learn about segmentation even in their OS classes. All right, so this is the reminder. Again, segment descriptor inside the GDT has a base address, which is 32 bits, and that's typically set to 0, and a segment limit, which is 20 bits, and that's typically all ones, all Fs, in order to say this is the maximum size. So typically you go from 0 to 4 gigabytes, cover all of memory with one big segment. And so what we're going to be doing is we're going to be changing the base address to not be 0, but still cover all 4 gigs. And that leads to an interesting condition where you can actually vector to negative addresses, negative to your 32-bit offset. You basically just wrap around so that the base plus the offset is greater than 4 gigs, and it just wraps around the space, and you end up at a lower address. So I'm pretty sure that's kind of a hardware buggish thing. I don't think that should be possible.
They used to do that in RealNode. They used to use the modular aspect of RealNode. I'll send you an article about it.
Okay, yeah. Let me know that. Well, they may. Well, okay. So they were actually using that as a feature to wrap around the thing? Oh, excellent. Yeah, definitely want to see that then. All right, so you can start at a base that's non-zero, add the 32-bit offset, and you'll get whatever address you want. So this, again, is the interrupt. You got segment selector, where we're going to now choose a new segment with the non-zero base and plus the 32-bit offset that's already there. We're not going to change that anymore. And then we're going to go to whatever code we want. So this is the sort of picture I use where let's say that an existing IDT entry has the logical address specified by the top. So it's got segment selector 8, and that's, again, you have to break down the segment selectors, and you'll just see that that's pointing at the entry 1 in the GDT, which has a base of 0 and a limit of FFF. So 8 corresponds to 1. So base of 0, limit FFF. So you choose 0 plus the 32-bit offset, and you get the linear address. That's your IDT before the hook is installed. With a normal IDT hook, you leave the segment selector the same. You modify the 32-bit offset, and then so 0 plus that equals the attacker's code, which is at F7D, whatever. When you were doing the segment selector hooking, you changed the segment selector to point at a new segment you put into the GDT. So you're kind of changing two things here. You change the GDT so that there's a new segment there that has a non-zero base. And you change the IDT so that you're selecting that segment. So this 280, this just corresponds to index 50 in the GDT. And so at index 50, I've created a new segment where the base is 77E blah, blah, blah. The limit is FFF, so it goes and covers all of memory space. And when you do the 777 plus the existing, like leave the 32-bit offset alone, so new segment base plus existing offset equals attacker's code. And the problem is that security software just looks at this 32-bit offset and it doesn't see that anything's different. So you can hook any of them. So for instance, Shadow Walker, it shows up like a red light, interrupt E is hooked, right? But you could just instead change the segment selector and still go to their code, but no one would notice that it had changed. And so then this last one is just an example where, let's say because I didn't have, I wanted to keep going with the convention of the linear address I'm targeting is F7D21, blah, blah, blah. So if I want to go to an actual negative offset, I can say, all right, I'm at F7E is what's already in here. So let's say that I just happen to show up and there's an address in the IDT that's already higher than my address. So I can't just use, base plus address, as a positive offset. I need it to wrap all the way around the 4 gigabyte space and be a negative offset. So the existing one's at F7E. I want to get to F7D. And so when I add FFF0, this will wrap around and I'll successfully get to F7D. So the important thing is treat logical addresses like logical addresses. Verify the full 48 bits, not just 32. And there's other things you want to verify in the IDT anyway, so you should really just verify the entire IDT descriptor so that people don't change the DPLs, the descriptor privilege levels on you. I hypothesize, there may be an attack very similar to this dealing with the sysenter. So the sysenter MSR, as we said before, there's one sysenter MSR for a segment selector. And there's one for the EIP. And we said people normally change the one for the EIP. The problem is the way the sysenter works and the assumptions it makes about a zero-based segment. I think right now it looks like it's not possible because implicitly, whenever I select a new segment selector, and this is pushing way back to the intermediate x86 class, the segment selector is going into a segment register. It's kind of, you think of it like going into a segment register, and then the segment registers had the visible part, which is the 16-bit part, but then they had a hidden cache part. They had the hidden part of the segment selector where they just copy whatever data was in the GDT out to the hidden part of the segment register. And the issue is, in the case of sysenter, it doesn't look at what I put in this CS MSR. It doesn't look at it, go to the GDT, copy that stuff into the hidden part. It actually just directly writes 0 into the hidden part, writes FFF into the hidden part. And so it may not be possible. It depends on one little quirk that I was asking Intel about, which they don't seem to want to answer. So, anyways, this is my little variant on IDT hooking, which bypasses most of the stuff right now, and I've sent emails to people telling them to fix it. All right, so let's take a quick 5-minute break, and then I'm going to cover all of the changes made by all the chaff things that I installed, as well as the individual changes by the rootkits. So we'll kind of talk about, we'll talk about what all there was for you to detect inside the VM, and then after that we'll let you loose. We'll do some teardown. We'll probably be, 1.5 hours early. early today, and so that means you'll actually have some lab time. So you'll be able to run these tools on your VM to find more stuff, as well as run the tools on your physical systems to hopefully not find stuff, but if you find stuff that could still be useful as well. So let's do a 5-minute break.